All right, so we have Andrea talking about blue monsters.
Okay, so good morning, everybody. And first of all, thank you very much to Avishai and George for having me here. It's been a very interesting meeting so far, and I'm looking forward for the next days. So today, I'd like to talk about something that we touched upon in the first 2 days of the workshop, that is the super early galaxies that JWST is observing, and which I call blue monsters for reasons that I'll explain in this slide. So clearly, it appears that this is one of the most exciting discoveries of JWST, that the telescope has seen a number of very luminous galaxies already larger than 10. These galaxies not only are luminous, but they tend to be massive, with stellar masses of the order of 10 to the 9, in some cases even larger. Most importantly, they tend to have blue colors. This is strange for our common conception, in which we try, or at least I try, I usually tend to associate big galaxies with red colors. In this case, we have blue colors. That's why I call them blue monsters. They are big, and particularly big for the time at which we see them. That is only half a giga-year after a Big Bang. Now, 4 of them have been searched for with ALMA, and particularly people have looked at oxygen 3 88 micron line and dust continuum, and so far none of this observation has been able to detect the galaxies that were targeted. Now, this is particularly, it may require some thought, and for example, you may read possible interpretation in this paper by Kohander et al. 2023. Recently, this is still unpublished, we are preparing it, we also got observation of GNZ11 with NOEMA. We had about 80 hours of observation on dust continuum, and we have been able to put a very stringent upper limit on the amount of dust there is in this galaxy, which is less than 13 microjansky. So essentially, we were very surprised by that, but this is what we found. So okay, so these galaxies are blue, and then so we may ask why they are so numerous, and this is a question that we have asked so many times already at this workshop. So if you want to have a possible solution to increase the luminosity, the UV luminosity of these galaxies, you have to remember that this quantity is proportional to 3 terms, the product of 3 terms. The first is the star formation rate. The second is conversion of star formation into UV light at 1500 angstrom. And also there is attenuation by dust. Okay, so what you can do in order to increase the luminosity is to increase the star formation efficiency, something that Avishai has just discussed, or you can also have stochastic star formation rate. For the increase of UV production efficiency, you can play around with the IMF, or you can change the type of stars you're using. For example, you can use pulsar stars. I'm not particularly in favor of this, but this is my personal opinion, mostly because we see that these galaxies have relatively high metallicities of the order fraction or half a solar, and we see particular traces of lines like helium-2 that are associated with pulsar stars. So at least for today, I will not discuss anything about that. And third is my favorite twist is to reduce dust attenuation. But before I discuss 3, I want to stop by 1, and because Avishai has already discussed the star formation efficiency, I'd like to concentrate for a second on the stochastic star formation rate. Now, there's been suggestion, and in particular by Shen, but he also, Guo Chao talks later on, that if you have a bursty star formation, then what you get is something like an Eddington bias effect, by which you convolve the luminosity function with the fluctuations, and you get a boost of the luminosity function at high luminosities. Now, the boost is quantified with respect to the continuous luminosity function that you would get if there are no fluctuations by the standard deviation in UV magnitude terms. So that goes from 0, no bursts, no stochastic star formation, and as you increase this standard deviation of the fluctuation, then you can reproduce the data. This is an interesting suggestion. So we said, okay, let's see what happens in simulation. So we have simulation, we have the Serra simulation set that Viola Gelli also discussed yesterday. And so we have 243 galaxies. These are zoom-in simulation, 10 parsec resolution, redshift 7.7 up to redshift 11, essentially. So we look at galaxies, and this is an example. This is one galaxy with stellar mass of 10.2 in log. So this is a star formation rate as a function of time. And so we subtract the continuum, the continuum level of star formation, and so we got the residual are the fluctuations, and this is the PDF. So you see that for this galaxy, the standard deviation is 0.19, and we repeat this exercise for all the 243 galaxies, and this is what we got. So this is the level of the fluctuations in terms of the stellar mass of the galaxy. So we find that the fluctuation level in star formation rate is 0.24 dex. Now, if you want to go into the previous plot, you have to transform this star formation and fluctuation in a UV magnitude fluctuation. There's a factor of 2.5 in between. So we find from simulation that our preferred value is 0.61. Now, if this is the value, does it help? In that case, we find that this is the curve that we get from this value. So if we add stochasticity, this is not sufficient, okay? So it's not enough. So stochastic star formation is there, so we confirm that this is true, but it cannot provide the observed luminosity function boost. Now, this is what we are finding. We are open to discuss the results, but clearly is something that apparently does not help. So let me turn to my favorite explanation then, to increase the UV luminosity, then what you can do, you can reduce the dust attenuation. Why did I come up with this idea? Well, this is the graph that inspired me. So, because we put together all the, for all the galaxies for which we have data from JWST and also rebels at various redshift, we made a plot of the AV, the attenuation in the visible versus redshift. And so you see that moving from rebels, redshift 7 or so, up down to the JWST galaxy, there's a clear decreasing trend that is shown in the plot. So I asked myself, do luminous galaxies become dust-free at redshift larger than 10? So that's the original question that I have, inspired by data. And so then I said, okay, but why aren't they obscure? Why are they dust-free? So I started to do a very simple calculation. So I took my favorite galaxy, for reasons that I will explain if you're interested, G8Z2, which is a photometric candidate at redshift 12, but for which we have a very good SCD fitting. For example, the stellar mass is 10 to the 9.2. So if you say that ratio of dust to stars is 1,000, as we usually assume, then you would expect this galaxy to have 3 times 10 to the 6 solar masses in dust. Now, the size of this galaxy is very small, typically of the order 100 parsecs. So let's say that it's less than 500 parsecs. Then if you put that dust into that region, then the optical depth that you would get is of the order of 25. Okay? So that galaxy should be totally obscure. You should not see it in the UV. However, what we observe for this same galaxy is 0.01. So that means that the opacity is 2,500 times less opaque. Okay? Oh, just a spherical distribution. We have a ball. This is a simple estimate. Okay? So where is this dust? the dust must have been produced by the stars, but it's not there. So I said myself, what could be the solution? The only possibility is that dust is ejected by radiation pressure. So I started to study this idea, and then I remembered that actually dust can help a lot the radiation pressure to act on the gas. Because differently from what is happening when you consider quasar, for example, or you consider the Eddington luminosity, this is the standard expression for the Eddington luminosity, which involves the stellar mass and the Thomson cross-section. But if you have a dusty flow, what happens is that instead of having the Thomson cross-section here, you have the cross-section for dust extinction, which is about 500 times higher than the Thomson cross-section. So that means that dust is much more effective in absorbing UV radiation and get the momentum the photons are transferred to the dust, which is transferred to the gas. So it's very easy to develop a wind. Now, it turns out that the parameter that we're interested in is this Eddington parameter, which is the luminosity of the galaxy divided by this effective Eddington luminosity, in which we have now substituted A times sigma t instead of sigma t. Now, it turns out that this parameter involves the luminosity and the Eddington luminosity. So the luminosity is proportional to the star formation rate. The Eddington luminosity is proportional to the stellar mass. So lambda E is just a different way to write the specific star formation rate. So what matters is the specific star formation rate. Good. So now, if we take all the galaxies that we have a redshift larger than 6.5, and we plot them as a function of this parameter, or, as we have learned, the specific star formation rate, so it's a one-to-one translation here, then we see that galaxies that have larger Eddington parameters have lower optical depth. This is just an empirical fact. There is nothing, there's no theory essentially there. We just add a compilation and put it into this graph. So that means that galaxies that are in the region where the outflow is expected, so in some sense they are super Eddington when you have dust, and this threshold, which is about 25 inverse gigayears, so whenever you have a galaxy which has a specific star formation range larger than this value, then it becomes super Eddington. And super Eddington means it drives an outflow. Good. So now, what I did is just to build a model that includes these ideas. And it's very simple. Probably it's even, Avishai simple, it's embarrassing simple. I said it's even more than that. But now I write the star formation rate like this. So the efficiency times the halo mass times the baryon fraction over the free fall time. I agree, Avishai, the free fall time is the key. I'm very convinced. And in fact, then the rest, you can write the free fall time for any perturbation, which it turns out to be a fixed fraction of the Hubble time. You can compute the stellar mass simply by multiplying star formation rate by the free fall time. And then you compute what I'm interested in, the specific star formation rate. The specific star formation rate turns out to be a very simple expression. It increases like 1 to 3 halves. And I also had computed the outflow velocity due to the radiation pressure. So we have learned that whenever this specific star formation rate becomes larger than this threshold value of 25 inverse gigayear, then there is a wind, and the velocity of the wind depends essentially on this ratio, a little bit on the stellar mass, and also on the baryon load of the wind. So what fraction of the baryons that are in the halo are involved in the outflow. This is a free parameter, and I'll fix it from observation, and I'll tell you in a second. So this is a simple model. Let's test it. Okay? Test number 1, star formation rate density as a function of redshift. These are the data, a compilation from McLeod 23, and the yellow curve is what the model predicts. So this is 1 plus z to the minus 7, more or less. Okay? So you see that the model does quite well for the star formation rate density. So test number 1 is passed. Test number 2, I convinced you that the specific star formation rate is what matters. Now, whenever the galaxy exceeds 25 inverse gigayears, then the galaxy drives a wind. So what is, on average, the specific star formation rate doing as a function of redshift? It grows, and this is the model prediction, and all the rest are the data. So the model prediction says that it grows like 1 plus z to the 3 halves, as I told you before, and it crosses this threshold for becoming super Eddington at redshift 10, on average. But of course, there is a scatter. The scatter that we see here at, say, between 8 and 10 in the specific star formation rate is consistent with that sigma, the standard deviation that was associated with the stochasticity of galaxies. So everything is falling in place. So the stochasticity that is producing a spread around the mean specific star formation rate. But on average, as you go to high redshift, more and more galaxies have a specific star formation rate that is high enough to drive a wind. What fraction of them are driving a wind? And this is, again, the model prediction compared to the data. So this is the fraction of super Eddington galaxies as a function of redshift. These are the data from Fiore et al. 23, and this is the model prediction. So test number 2 also passed. Test number 3 is, okay, you're telling me you're predicting outflows, but do we see these outflows? So with Stefano Carniani, which is the office close to mine in Pisa, and he's into the JWST collaboration, has written a very nice paper on the outflows in galaxies between redshift 3 and 9. And so the point, I've asked you, so please select galaxies that are super Eddington. That means they have specific star formation rate larger than this 25 inverse gigayear value. And all of them have an outflow from the width of the lines that is measuring. And from, so the points are the data from JWST. The curves are my model, essentially. And from here, I can fix the fraction of baryons, that parameter that I didn't know. So the fraction of baryons that are involved in the wind. And this is in the upper plot is the histogram. So this is, you see, the FM that I'm trying to fix. So, and this FM is the outflow gas mass with the halo gas mass. So what fraction of the halo gas is involved in the wind? And we see that there's a distribution, but typically at the order of a few percent. We go from 2 to 4, 2 to 6%. Okay, so, but what is important is that, as predicted, all the galaxies that are super Eddington indeed have an outflow observed. So I consider also this a very good test of the model. So radiation-driven outflows carry away a few percent of the baryonic halo mass that is comparable to the galaxy mass. So the galaxy is strongly destroyed or strongly affected by this radiative outflow. Now, the final thing that now we can predict is from the same model. I'm not changing anything. We predict the luminosity function, for example, redshift 11. So the yellow curve is the prediction that I made in the paper that I published exactly 1 year ago. At that time, I only had 2 galaxies, JHS2 and GNZ11, which are the two circles here. All the other points were not existent. So I put them essentially through during the last year, and you see that the yellow curve that assumes that these galaxies have ejected their dust in the wind, this luminosity function does pretty well. And so if instead I would have allowed the dust that has been produced by the stars to stay there in the galaxy, I would have got the purple curve. And you see there is a 1.5 Dex difference in density, number density of galaxies. So the conclusion is basically that if dust in super early galaxies is cleared by outflows, then the number densities are explained, and I don't need large star formation efficiency, even though for me, it's not a problem if the star formation efficiency is high. For me, the problem is just to make this galaxy is massive and blue. Okay? So I need to get rid of the dust. Finally, the final implication is something that Viola has already discussed in her talk. So there's also the fact that these outflows induce a quiescent phase or a lull phase in the galaxy itself. And so we have seen already, Viola showed that for this quiescent galaxy found in jades, the star formation history deduced from SED fitting is such that there's a short burst followed by a very rapid quenching that supernova, she showed, cannot produce. So supernova cannot make such a rapid drop. It must be something else. Now, it is true that in the simulation we do find quiescent galaxies that actually have their star formation rate quenched through supernovae. But the drop would be much more gentle rather than sharp. So simulation had a problem. However, if we assume that these galaxies may develop an outflow, then it could be much faster. And to convince you of that, let me take a specific case of this galaxy, Loser 23, Jades, blah, blah, blah. So it has a stellar mass of 10 to the 8.7, a star formation rate when it is at the peak here of 15 solar masses per year. So it means that at that time, when it was active, then the specific star formation rate was 30 inverse gigayears, larger than my favorite value, 25 inverse gigayear, above which the galaxy develops an outflow. And so I think that during this stage, the galaxy developed the outflow and pushed away all the gas, and it got quenched. And not only the gas, but also the dust. In fact, you see now, there's very little dust in this galaxy, 0.1 magnitudes. And so this is something that goes together. And so the outflow can also cause this outflow during the bursty phase, and the outflow quenches the star formation. So the velocity that I predict for the burst, for the wind developed by this burst, is about 500 kilometers per second. Keep in mind that the effective radius of this galaxy is 36 parsecs. So 36 parsecs divided by 500 kilometers per second, in 0.07 megayears, the galaxy is gone. This is my summary. Radiation-driven dust outflows are also unavoidable at high redshift because the specific star formation rate goes up on average, plus the scatter due to the stochastic star formation rate. The outflows clear the dust from early massive galaxies, making them blue and abundant because they become brighter. And they also temporarily abruptly quench star formation, making the galaxy quiescent. Thank you very much.
I think a great talk. I'm going to actually ask one myself as an observer because I was looking at some of your numbers, and at some point you're distinguishing between AV of 0.1 and 0.01. What's the difference in star formation rate or UV luminosity in such a small range?
I don't know where I'm referring to.
You had a diagram on the left, and you were talking about Rebels galaxies and some other galaxies.
Oh, okay.
AV of 0.1 and then 0.01,
yeah,
which is super precise. And I was wondering what's the difference in the UV luminosity to make such an impact.
So you're referring to this plot, right?
Yeah. Just curious about that.
But this is, so on average in Rebels we find of the order 1, AV of the order 1 or half. And then, however, if you look, for example, these galaxies, they're around 0.01, right? So there's a factor of 100 change. Oh, these ones. Yeah, these are different determinations. They're still Rebels, but with different determinations, so there's uncertainty.
Yeah, so I was wondering if one of the predictions of your model was that the beta, the UV slope, should show some, sudden tendency towards very negative values as you get above some threshold in UV luminosity, right? Because if you're cleared out all the dust.
Mm-hmm.
Is that-
Yeah,
is that a
I think
prediction?
first of all, as you I said, I mean, the specific star formation rate grows with redshift. So it's a continuous process that is more and more galaxies are becoming super Eddington. And therefore, those galaxies are able to clear the dust through the outflow. Actually, I have to say that clearing doesn't mean that you have to eject the galaxy to infinity. The only thing you need is just to move or expand the dust layer so that the optical depth drops. Okay, so the dust could be in the CGM or in the surrounding. You don't need to have anything particularly dramatic. But it's clear that as soon as you go to higher redshift, more and more the fraction of super-Eddington galaxy becomes higher, and therefore you would expect the fraction of blue galaxy to become higher as well, which is what you see here.
But at a given redshift,
Yes.
you see the only things that should be cleared are the things above 25 ERZ-verse, right? And those are really the brightest UV things. So if you plot beta versus UV luminosity, there should be, once you get towards, the very brightest UV magnitudes, you should get a drop from beta towards very negative values, I would think, in this model.
Yeah, so what I'm saying is that, for example, the galaxies that are above this threshold, they should tend to have bluer luminosities with the blue slopes with respect to, yes, that's correct, yes.
So has this been observed? I thought they had plots of beta versus UV luminosity.
Well, you can, from the previous, from the, not at this very high redshift, because, yeah. If you look at, well, anyway, we can discuss it later.
So I'm a bit confused because we understand the idea of like radiation-driven outflows based on dust opacities. But there are recent works by Mark Krumholz's group, Shyam Menon, and Mike is here. So they find that if you have enough surface density, you actually don't even drive radiation-driven outflows. So what's happening?
If you have what?
Enough surface density of gas, you're not able to drive radiation-driven outflows. So it's like if you have more dust, you cannot drive outflows.
The point here is the following, that these objects are very compact. So they are so compact that they behave like stellar quasars, right? Because they are almost point sources, they have sizes of 30 to 100 parsec, in which you have a very high luminosity, and therefore, and all it's a spherical symmetry that it's a very simple system in which it's a bit like quasar work.
Yeah.
The only thing.
I understand the concept. I'm just wondering, like, what's the difference between these two things? Maybe Mike can comment on that.
So I don't think it's correct to say that you can't drive an outflow in a high surface density system dominated by rays of feedback. You'll always get your outflow. It's just that you have to form a lot of stars before you get that anyway.
Exactly.
So you gotta get to a certain star formation state to see it. But that gas is gonna fly eventually. But you're always gonna overshoot to the point where you still super end. So I don't think the pictures are necessarily intentional.
But how do you separate it from supernova-driven outflows to the radiation-driven outflows? Even in this galaxy, how do you separate?
Well, what I'm saying is, I don't know. I think that the supernova, well, there are also papers that have been looking at supernova winds in exactly in these galaxies by, I guess, also Beam and Nat is looking to that. But they find that essentially because the density are so high, it's the same reason for which Avishai and you are protecting the clumps, because the density are so high that the supernova remnants got radiate away their energy very rapidly, and therefore they cannot truly expand, so they deflate almost immediately. But the thing that I see is that these are jade galaxies, and they're all the galaxies that have this ratio larger than 1, so they have super Eddington, they have outflow.
So it feels like this is a very active topic for discussion. I might have to cut you here because we still have one more talk and we're a little behind the schedule. But
Sure.
I'm sure we're going to talk about this in the discussion later in the afternoon. So if we can have the last speaker of the morning session. And let's thank Andrea, of course, again. Thank you.